We now consider the scattering matrix representation of microwave networks. Representation of microwave networks by impedance or admittance matrix is not very convenient, as at microwave frequency the voltage, current or impedances cannot be measured in a direct manner. The quantities that may be measured easily are reflection coefficient and transmission coefficient, and this forms the basis of scattering matrix formulation. The scattering parameters can be measured directly from instruments called network analyzers. So, let us consider an N port network, and at the nth port let us define the parameter A n, which is voltage V n plus the incident voltage at the nth port normalized with respect to square root of Z0 n, the Z0 n being the impedance of the nth port. Similarly, we define B n is V n minus divided by root Z0 n. So, to illustrate, let us consider a two port network. So, these parameters A 1 and B 1, they are the incident and reflected parameters. They represent the incident and reflected waves in port 1. Similarly, A 2 B 2 represents the incident and reflected waves at port 2, and we can write the reflected waves B 1 as S 11 A 1 plus S 12 A 2. Similarly, B 2 S 21 A 1 plus S 22 A 2, and this can be written in the form of matrix B S A. Now, this S matrix, it is the scattering matrix for this two port network. Now, we find that S11 is actually B 1 by A 1 when A 2 equal to 0, and therefore, it represents V 1 minus by V 1 plus at port 1 when V 2 plus is equal to 0, and this is essentially the reflection coefficient at port 1 when no voltage is incident at port 2. Similarly, S 22 is the reflection coefficient at port 2, and S 12 and S 21 will be the transmission coefficients from port 2 to 1 and from 1 to 2. Now, the voltage at the nth port, it is given by V n is equal to V n plus V n minus, and in terms of the parameters A n and B n, we can write V n to be equal to root Z0 n A n plus B n. Similarly, the current at the nth port is defined as 1 by Z0 n V n plus minus V n minus, and therefore, we can write I n to be equal to 1 by root Z0 n n minus B n. And if we calculate the power flow at the nth port, then it is half real part of V n I n conjugate, and when we substitute V n and I n, we get P n is half real part of A n plus B n and A n minus B n conjugate. when it is expanded, we can write in this form n conjugate minus bn conjugate plus n conjugate bn minus bn conjugate n. Now, this term can be shown to be purely imaginary, and therefore, we can write P n is equal to half A n n conjugate minus bn conjugate. Now, this term half n conjugate, which can be written as mod V n plus square divided by Z 0 n, it is the power carried to the nth port by the incident wave. Similarly, half bn conjugate is V n minus magnitude square divided by 2 Z 0 n, it is the power reflected back from the nth port. Now, let us discuss the symmetry property of S matrix. Now, we have already seen that for a reciprocal network, Z matrix is symmetric. Now, let us start our discussion with the assumption that all the port impedances are the same, that means Z 0 n is equal to Z naught. So, we can write V matrix as V plus and V minus, and I matrix we can replace by 1 by Z naught V plus minus V minus, and that can be written as Z dash V plus minus V minus. So, if we rearrange the terms, that means we take V minus terms in one side and V plus terms on the other side, then we can write this U is the unity matrix, and similarly, when we have all the port impedances are same equal to Z naught, the scattering matrix B is equal to S A, this term can be written as V minus S V plus. And from this term above, we can find V minus to be equal to Z dash plus U inverse into Z dash minus U into V plus. If we compare these two, then we get S equal to Z dash plus U inverse into Z dash minus U. So, this expression establishes a relationship between the S matrix and the Z matrix, rather Z dash matrix, where we have normalized Z matrix by Z naught. We can also have a alternative form of representation for the scattering matrix. We can derive it like this. At the nth port, we have V n is equal to V n plus plus V n minus, and I n is 1 by Z naught V n plus minus V n minus. So, we can find out the expression for V n plus and V n minus from these two, and then we can write V n plus as half the voltage matrix for the incident wave V plus is equal to half Z plus Z naught u I, and similarly for the voltage matrix for the reflected wave we can write in this form. Now, from these two relation we can find S, the scattering matrix So, once we make all these substitutions, we finally get the expression for S, which is S is equal to Z dash minus u multiplied by Z dash plus u inverse. So, this is another expression for scattering matrix S in terms of this normalized impedance matrix. And from our earlier derivation we got this expression. Now, since Z dash and u, that these two matrices are symmetrical, so if you take transpose of this, then we can find S is equal to S transpose, because once you take the transpose of this matrix, this inverse transpose will be same as the inverse for a symmetric matrix, and Z dash minus u transpose will be equal to Z dash minus u. From this we can find that S is equal to S transpose, and this shows that the scattering matrix for a microwave network is symmetric. We can also show that when all the port impedances Z0 and are different, then also this property holds. So, in order to show that, we write V n bar to be equal to V n plus V n minus divided by root Z0 n, and this is actually A n plus B n, and in the same manner I n bar becomes A n minus B n, and we introduce two square matrices. One is a matrix of root Z0 n, which has all the diagonal elements as root Z0 n and off diagonal elements are 0, and another matrix where the diagonal elements are 1 by root Z0 n. Now, if we introduce these two matrices, we can write the voltage matrix V can be related to normalized voltage V bar, and similarly current matrix I can be related to normalized current matrix I bar. And this equation V matrix is equal to Z matrix into I matrix can be written as shown here in terms of the normalized voltages and currents, and then we find that this normalized voltage matrix is related to the current matrix in this manner, where we have a matrix root Z0 n inverse, then the matrix Z, another matrix 1 by root Z0 n. So, we denote this as Z bar, and therefore, we have now V bar is equal to Z bar I bar. Please note that this matrix Z bar is symmetric, because the component matrix Z0 n, 1 by Z0 n, Z, they are all symmetric matrices, and Z bar is the product of these symmetric matrices. So, we can relate the normalized voltage matrix to matrices A and B as shown. Similarly, the normalized current matrix can be related to matrices A and B as A minus B equal to I bar. Now, V bar can be replaced at Z bar I bar, and then we replace I bar, and then rearranging the terms, we can write B to be U plus Z bar inverse into Z bar minus U A. Now, this essentially gives the S matrix, the scattering matrix S, in terms of the unity matrix U normalized Z matrix. Now, since U and Z bar they are symmetric, S is also symmetric, and therefore, for any linear and reciprocal network, that is where Z matrix is symmetric, the scattering matrix S is also symmetric. Now, let us consider the scattering matrix representation for a lossless junction. By a lossless junction, we mean that whatever power it enters the network through different ports, same power will leave the network, and we have seen that the power in the nth port P n is given by half A n n conjugate minus B n conjugate. This is the incident power and this is the reflected power. So, when the junction is lossless, total power leaving all n ports must be equal to the sum of the incident powers, and we will have sigma P n equal to 0, and from there we can write summation of B n conjugate is equal to summation of n conjugate. Now, since we have B is equal to S A, we can write B n to be equal to sum of S n I A I. So, B n is the nth element of the B vector, and that can be obtained by multiplying the corresponding nth elements of nth row with the elements of vector I and summing them over I to n. And then if we substitute here in this expression B n and B n conjugate, then essentially we will get modulus of summation of S n I A I square, and this side we will get summation of A n conjugate. Now, these parameters A n, these are the input parameters, and therefore, they can be chosen independently, and if we set all the n's except A I to be 0, then this equation what we have written reduces to this. So, it becomes, this summation becomes mod of ai square, and this summation it becomes a single term Sni ai magnitude square. And therefore, what we see that summation of Sni square, which is actually summation of Sni Sn conjugate, is equal to 1. Now, this Sni essentially represents the element of the ith column of the scattering matrix, and this is the conjugate of the elements of the ith column, and therefore, we can write that the dot product of any column of scattering matrix S with the conjugate of that of the same column gives unity. And please note that here this I may take any value from 1 to n. So, this relationship will be held for any column of the S matrix. Now, let us consider another property of the scattering parameters of a lossless junction. Now, in this case, what we do? We consider AS and AR to be non-zero and all other ANs are 0. Then from this equation, if we expand, we can write summation of 1 to n SNS AS plus SNR AR magnitude square, and on the right hand side it becomes AS S conjugate plus AR conjugate, and this becomes A square plus AR square. So, if we expand this product terms, then we find that we will have terms like summation of small n is equal to 1 to capital N mod of SNS square mod of AS square. Now, this summation of mod of SNS square, as we have seen, it will become 1. So, we will have mod of AS square. Similarly, product of these two terms will give mod of AR square, and that will get cancelled with these two terms, and making this simplification, from this expression we will get a relation of this form, which is summation of 1 to n SNR AR SNS conjugate S conjugate is plus SNS AS SNR conjugate AR conjugate is equal to 0. Now, since AS and AR they are independent, if we choose AS equal to AR, and from this relation, so in this equation when we substitute AS equal to AR, we get summation of SNS into SNR conjugate plus SNR into SNS conjugate is equal to 0. And if instead we choose AS is equal to J AR, that means with AR equal to real, that means this is AS is purely imaginary and AR is real. If we choose AS and AR in this form, then we get another equation, and we get summation of SNS SNR conjugate minus SNR SNS conjugate equal to 0. Now, in this equation you see that we are getting the sum of these two terms, and here we are getting the difference of these two terms, and in the both cases right hand side is equal to 0. So, neither AS nor AR is 0. The above two conditions can be satisfied only if we have summation of SNS SNR conjugate is equal to 0 and S is not equal to R. So, this can be put in this form. Therefore, we find that the dot product of a column of the scattering matrix of a lossless junction with the complex conjugate of any other column is 0. So, only condition we require is that S is not equal to R, that means the two columns are to be different. Now, whatever we discussed so far regarding the properties of the lossless junction, this can be derived using a different approach, which is as follows. We have for a lossless junction summation of Bn Bn conjugate is equal to summation of N N conjugate, and therefore, this term is essentially transpose of B into B conjugate, and similarly N N conjugate can be written as transpose of A and A conjugate. Now, if we substitute B to be equal to S A and then we take the transpose, we get A transpose S transpose S conjugate A conjugate equal to A transpose A conjugate. That means, this term will be a unity matrix. So, S transpose S conjugate equal to U can be written as summation k equal to 1 to n S k I S k j conjugate is equal to delta I j. Now, this delta I j is equal to 1 for I equal to j and delta I j is equal to 0 for I not equal to j, and therefore, whenever I equal to j, we can write k is equal to 1 to n S k I conjugate is equal to 1. So, this is the condition we derived earlier. This essentially represents the dot product of the elements of one column with the conjugate of the same column, that means the ith column, and when I is not equal to j, that means the columns I and j are different. In that case, if we take the dot product of the ith and jth column S k I and S k j conjugate, then this summation becomes 0. Now, let us consider one example to explain some of the things that we have discussed in this lecture. So, we take this example scattering matrix for the junction of two transmission lines. So, it is shown here. Here you can see a junction between two transmission line. This transmission line has a characteristic impedance of Z1 and this has characteristic impedance of Z2, and this is S11 and S22, these are essentially the reflection coefficient at the junction, and S21 and S12, these are the transmission coefficient for the junction. And let us find out these S parameters, S11, S12, S21, S22. So, we have B1, B2, this is equal to S11, S12, S21, S22 into A1, A2. And from this matrix relation, we see that S11 is essentially B1 by A1 when A2 equal to 0. Now, we have defined A2 to be B2 plus divided by root Z0 2, or here it is Z2. So, when A2 equal to 0, it means V2 plus is equal to 0. So, we can write similarly B1 can be written as V1 minus by root Z1, and A1 can be written as V1 plus divided by root Z1, and hence S11 we can write as V1 minus divided by V1 plus when V2 plus equal to 0. Now, if we take this junction, we can write the voltage on the left hand side of the junction, it is V1 plus plus V1 minus. On the right hand side of the junction, we have already argued that V2 plus is 0. So, we can write V1 plus plus V1 minus is equal to V2 minus, and if we equate the currents, then we can write 1 by Z1 V1 plus minus V1 minus, this is equal to V2 minus by Z2. And therefore, rearranging the terms, we can write V1 plus plus V1 minus is Z2 by Z1, V1 plus minus V1 minus, and therefore, S11 which is V1 minus divided by V1 plus when V2 plus equal to 0, this can be put in this form Z2 minus Z1 divided by Z2 plus Z1, and this is same as the reflection coefficient at the junction. And if you proceed in the same manner, you can show that S22 is equal to Z1 minus Z2 divided by Z1 plus Z2, and this is equal to minus S11. Now, let us evaluate S21. S21 is B2 by A1 when A2 equal to 0, and this can be written once we substitute B2 and A1, we can write B2 is V2 minus by root Z2 and A1 is V1 plus by root Z1. So, it can be written as S21 is equal to root Z1 by root Z2, V2 minus by V1 plus for V2 plus equal to 0. So, we have seen that V1 plus plus V1 minus is equal to V2 minus, and from the current relationship we can write 1 by Z1 V1 plus minus V1 minus is equal to V2 minus by Z2, and this can be, once we take Z1 in this side, we can write in this form. And therefore, if we add these two, we get 2 V1 plus is equal to 1 plus Z1 by Z2 V2 minus, and therefore, V2 minus by V1 plus when V2 plus is equal to 0 is 2 Z2 divided by Z1 plus Z2. So, now we have this part evaluated, and S21 we get by scaling this with root Z1 by Z2, and then we get S21 equal to 2 root Z1 Z2 divided by Z1 plus Z2. And since this junction is a reciprocal junction, we will have S12 equal to S21. We now consider a second example, where what we do, we find the reflection coefficient at the port 1 of a 2 port when the port 2 is terminated to a short circuit. So, let the S parameter for the 2 port be given as S11, S12, S21, S22, and next what we do in this 2 port, we connect a short circuit at the port 2. So, when we put a short circuit at the port 2, V2 becomes 0 and V2 is V2 plus V2 minus. So, when this term becomes 0, essentially A2 becomes equal to minus V2. And now, if we take this V2 is equal to S21 A1 plus S22 A2, this can be written as minus A2, and from here we can solve A2 equal to minus S21 divided by 1 plus S22 A1. And if you consider B1, then B1 is equal to S11 A1 plus S12 A2. So, the reflection coefficient is V1 minus divided by V1 plus, which is B1 by A1 and can be found as S11, and we replace A2 by this term. So, S11 minus S21 divided by 1 plus S22.